we have a sum. The sum from 0 to infinity, e to the n plus n factorial upstairs, e to the n times n factorial downstairs, and then we're asked, what does this equal? Now, we have some problems here. Well, we have a problem, that's true. But when I say we have some problems here, this sum is not geometric, because there's some n's that aren't in exponents. Okay. It's also not going to look very promising for telescoping, because for telescoping you kind of have to have something minus something that's very similar. Just shift it a little bit. We don't have that going for us. So we have to talk about a third route, and that's going to be Taylor polynomials. All right, so anyways, we have this sum. We have 5 options. 1 over e times e minus 1, 1 over e minus 1, e over e minus 1, e squared over e minus 1, e cubed over e minus 1. You've had a few minutes. Is there an answer? Sorry, what? D? You sure?
I think so.
Okay. You're right. The answer is D. E squared over e minus 1. All right. So what can we do? Well, we'll take advantage of the plus. Now, there's good pluses and there's bad pluses. Things upstairs, outside of functions, those are your good pluses. And it says, hey, let's break it up into 2 things. So we'll have e to the n over e to the n factorial, in which case the e to the n's cancel. And then we'll have n factorial over e to the n times n factorial, in which case the n factorials cancel. And so now we have 1 over n factorial plus 1 over e to the n. And then we say, okay, let's continue to take advantage of our pluses. So now, instead of thinking this as one sum, we'll break it up into 2 sums. 1 over n factorial and 1 over e to the n. All right, now 1 over e to the n, that's probably the one that's a little bit easier for us to think about, because it feels geometric, things to the nth power. And we can write this as the number 1 over e, all of that raised to the nth power. And then we say, hey, this is geometric. We know what x is. We have a sum for that. Now, what about 1 over n factorial? Well, we start thinking, saying, hey, have we ever seen anything that looks like something over n factorial? And if we were to go through, I happen to have here my convenient list of Taylor series. You say, what looks like something over n factorial? And say, hey, there's something over n factorial. So what do we say? It's like, well, if we can just make the top look like 1, we win. Well, the top looks like something to the n. And then we're like, aha, 1 to the n is 1. And then that says, well, we can put that in. That gives us e. And so we did our sums. And then we just do a little bit of algebra. We add these together. And so nothing too exciting from there. And you end up with e squared over e minus 1. All right. So that's the answer. Any questions on this one? Okay. Well, we'll get to do a similar one in just a moment. Our thought for the day, another Japanese proverb. We had one earlier this semester. And I'll try to say this. Tada yori takai mana wa nai. But nothing is more costly than something given free of charge. And I wanted to maybe use this in one of our times when we talked about AI. Because I feel that this is an important thing to keep in mind. Although I also am a little bit nervous because somebody might say, wait a second, Steve, don't you post online free videos? What? No. So let me explain what I think this means to me, at least right now. it's easy to go to something like AI and say, I'll put something in, and I'll just cut and paste the answer, and then it's like, I learned, or I did the assignment. But did you learn? I don't know. Most often not. And the problem is that it's this sort of false sense of understanding. You have to put in the effort. Now, being free, of course, isn't just about money. It's also about time. Yes, there's a lot of good free resources, but you have to use them. You have to put in the effort. It's like the videos online. You can watch them, but if you're just passively watching them or listening to them in your sleep, you're not gaining the information you need. You have to put in the time. You have to put in the effort. It's only when you put in that effort that you end up succeeding. So be careful. Be careful. In some sense, if you try to shortchange yourself now and cut corners, it'll cost you down the road in your downstream courses. And Iowa State will have your tuition, but what will you have? We want you to succeed. After all, how are we going to get your money in the future if you're not a success, right? No, come on, no, that's not it. We want you to succeed because you deserve it. All right, goals for today, same thing as last time. We're going to continue talking about applications of Taylor series. We've already talked about finding a particular derivative. We've already talked about finding a Taylor polynomial. So we'll keep going down our list. And so next thing is we'll find some sums. Find the following. The sum, n equals 0 to infinity, negative 4 to the power n over 2n factorial. 2n plus 1 factorial. All right. Well, not so clear how to begin, perhaps. This is a case, and we say, maybe we can think about our Taylor series, and we play a game. If I were a Taylor series, what kind of Taylor series would I be, and why? So we have this sum, negative 4 to the n over 2n plus 1 factorial. What do we look like? Is there any clue? Sine? What makes us say sine? Yeah, we saw the 2n plus 1 factorial. And we said, aha, we saw the sine. And it opened up our eyes when we saw the sine. All right. So we say, great, this matches downstairs. So what we need to do is make the upstairs match and figure out, hey, what's in our box? And if we can figure out what's in our box, then we can go to the other side. So oftentimes we start here on the left and said, let's go to the right. But we can also start on the right and go to the left. All right, so looking at what we have, negative 4 to the n, what can we do to that to make it look more like this expression, negative 1 to the n times something to the 2n plus 1? Or can we do that? Okay, so we can separate here. We can say, hey, this is negative 1 to the n, 4 to the n. Yes? And now we're like, cool, we have our 2n plus 1 factorial. We have our negative 1 to the n. We have to have something to the 2n plus 1. Currently we have something to the n, 4 to the n. So we have to start thinking, what's another way to write 4 to the power n? Sorry, what? 2 to the 2n? Yeah, so we can note 4 is 2 squared. So I say, hey, that's an idea. If we replace this 4 to the n by 2 squared to the n, then what we really have is 2 to the 2n. All right. Are we ready? And why not? Yeah. Someone said, hey, you have 2n, you need 2n plus 1. So, what will we do? We'll put it there. Because we say, we really need it, so we're going to put it there. Are we allowed to do that? I mean, we really needed it, so it seems fair that we can just do it. If it's something that we really need. Well, we can't just arbitrarily put it there, but what can we do if we did want to put it there? Yeah, so subtract 1 in the exponent, which is equivalent to divide by 2. So what we can do is we can put a half out in front. Now that's the equivalent of like a minus 1 there. And 2 to the minus 1 is a half. And the half being a constant pulls out in front. So that's legal. Now, with all of that, what does this part become? Sine of 2. Because what's going on is we say, hey, we now have our box. And the thing inside of our box is a 2. So we can just say this whole thing is sine of 2. And so we have our answer. 1/2 times sine of 2. All right. That wasn't so bad. It's just a matter of saying, all right, can we spot the Taylor series? And it's a matter of oftentimes the factorial will give it away. If it's n factorial, you say, hey, you should think of e. 2n factorial, cosine. 2n plus 1 factorial, sine. All right. Well, that was quick. Let's try another problem. So, we're given a function called cosh x. Now, cosh is sometimes called hyperbolic cosine. It's e to the x plus e to the negative x over 2. And in terms of the power series, has a very nice power series. Also, I should say the Taylor series. It's x to the 2n over 2n factorial. And now you might say, oh, I kind of see why it's connected to cosine, because it kind of looks like cosine, except for one thing. What's the difference? This minus 1 to the n. So there's a reason we call it hyperbolic cosine. They really are closely related. In fact, they're so closely related, in essence, they're the same function. And what we're seeing is we're seeing two slices. All right, well, the details of that are a little bit complex, so we won't go into it. But all right, so we have that fact. X to 2n over 2n factorial, we know what that function is. And then we're asked to do the following. Find the sum from 0 to infinity, n squared divided by 2n factorial. All right, what can we do? And on a side note, this is an old final exam problem. So the good news, it's not your final exam problem. But maybe that's not good news. Maybe you're like, oh, I love this one. I wish we had it. So what can we do? What can we do? Any way that we can derive this answer?
Take the derivative.
A derivative. Ah, what makes you think of taking a derivative?
You can get the 2n downstairs.
Okay, so one thing you might say is like, oh, maybe I can just plug something into x to 2n to make it look like n squared. Unfortunately, there's not a way to do that. So it's not like, oh, there's a magical value of x out there. And we say, well, what do we need? Well, we need to have n's downstairs. And not this downstairs. In other words, we need to put some n's here. And there's an n upstairs right now in this exponent. And we're allowed to do manipulations. We've talked about things like add and subtract. We did that earlier. But we're also allowed to do things like differentiate and integrate. So we can take a derivative. All right. So let's try this. And we'll take a derivative of both sides. So the derivative of cosh of x is equal to the derivative of the sum. 0 to infinity x to 2n over 2n factorial. And this is valid everywhere because the series for cosh is built off the series for the exponential function, which is valid everywhere. Does anybody know the derivative of cosh, hyperbolic cosine? If you want, we'll just work with the e to the x plus e to the negative x over 2. It's e to the x minus e to the negative x over 2. And this has a name. It's called sinh, hyperbolic sine. All right. Well, how do you take the derivative of a sum? Take the derivative of a sum. You take the sum of the derivatives. The derivative can pass through the sum. So you say, okay, so we have the sum, n equals 0 to infinity, 2n, x to 2n minus 1 over 2n factorial. Now the 2 is not a problem. We can fix 2's. We have ways to do that. And so at this point we said, oh, if you plugged in 1 at this stage, you would have a 2n over 2n factorial. That's close. But is it close enough? Not yet. Not yet. But we're making progress. We have an n. What do we want to get to? N squared. All right, so how do we get to n squared? How do we get 1n? What did we do? We took a derivative. So how do we get 2n's? Yeah. It's an idea so nice, let's do it twice. Now, before we do it, I do want to talk about one little detail. This minus 1. We have to fix that. Because if we take a derivative next, we're not going to bring down 2n, we're going to bring down 2n minus 1. How can I change this 2n minus 1 to 2n? What do I need to do?
Add 1.
Okay, we can add 1. So how do you add 1? What does that mean to add 1 in this setting? Yeah, multiply by x. So what we'll do is we'll multiply both sides by x. So we get that x, e to the x minus e to the minus x over 2 is equal to, here, we're multiplying everything by x. The x can come in. Sum, n equals 0 to infinity, 2n x to 2n over 2n factorial. Now, we're ready to take another derivative. All right. Well, there's two sides, the left and the right. I'll take the derivative of one side if you take the derivative of the other. Which side do you want to do, the left or the right? Did you say no? Left? All right. What's the derivative of the left-hand side? What rule do you need? Product rule. So what do you write down? Product rule says take the derivative of the first, which is 1 times the second, plus the first, which is x times the derivative of the second, which is plus e to the minus x, because a minus minus makes a plus, over 2. All right, so I'll do the other side. Sum n equals 0 to infinity. We have 2n already. Another 2n came down. X to the 2n minus 1 over 2n factorial. All right, so here we took another derivative. Okay, we're close. We're really close. What can we do now? Do we have the n squared? Yes. There's other stuff, but we have the n squared, so we don't need to worry about more derivatives. Okay, so now that we have our n squared, are we ready to pick a value for x? And if we are, which value of x should we choose? Are we ready to pick a value for x? And which value for x do we want? 1? Okay. We'll plug in x equals 1. All right, so we have here, we'll have 1 times e to the 1 minus e to the minus 1 over 2 plus 1 times e to the 1 plus e to the minus 1 over 2. Okay, that's on the left-hand side. I think that simplifies. What does this become? Becomes e. On the other hand, we also have on the other side the sum 0 to infinity 2n 1 to the power 2n minus 1 over 2n factorial. Well, the 2n factorial downstairs, that looks great. What is 2n times 1 to the 2n minus 1? 4n squared. All right. Well, we're almost ready to write down our answer. In fact, we will. We'll say, great. At this point, we're ready to say the sum from 0 to infinity of n squared divided by 2n factorial is equal to
E over 4.
and these things have to match. We just have to fix that for e over 4. All right. So this is an example of using derivatives. Derivatives can bring exponents down, and it allows us to rewrite certain things. Any questions? Well, okay. In that case, since we had such a good time with derivatives, let's talk integrals. Find the Taylor series for f of x equals the integral from 0 to x of cosine of t squared dt. Okay. Now, is there a way for us to integrate cosine of t squared dt? Think back to before we started this portion of the class. If you were asked to integrate cosine of t squared dt, what's the appropriate response? Probably something along the lines, you fool, you madman, it's not possible. Or maybe some maniacal laughter, you know, it can't be done. We don't have the technology. But wait, that's because you're thinking about it as cosine t squared. But we have better ways. What can we do with cosine t squared? We can turn this into a polynomial. And polynomials are our friend. Okay, so let's talk about the following. So, remember when it says find the Taylor series, really all you have to say is I just have to find a series, and it's the series. So I'll start with the series and I'll manipulate it. So let's start with cosine of t squared. We know what cosine is. So what is cosine of t squared? Well, the answer is t squared is our box. We see what's in our box, so we say, well, that's the sum, n equals 0 to infinity, minus 1 to the n of t squared to the 2n over 2n factorial. And just make one more comment. Another way to write t squared to the 2n is t to what power? 4n. You multiply, when you have a power to a power, you multiply the powers together. So, we now say, well, if I want to do the integral from 0 to x of cosine t squared dt, that's the integral from 0 to x of the sum, 0 to infinity, negative 1 to the n, t to the 4n, over 2n factorial dt. And our punchline is to say, you know, when we differentiated, we did it term by term. When we integrate, we do it term by term. So it's really the sum from 0 to infinity. And the only thing I have to worry about is things with the t. So this negative 1 to the n, this 2n factorial, there's no t. There's this integral from 0 to x, t to the 4n dt. So we push the integral through the sum. And the good news is, while cosine t squared is hard, integral t to the 4n is not. What is the integral of t to the power 4n? It'll be t to what power? 4n plus 1, and then divide by 4n plus 1. And don't forget, it's a definite integral. Evaluate from 0 to x. So this becomes x to the 4n plus 1 over 4n plus 1, subtract 0. So we just put that in, and we say, okay, so this becomes the sum, 0 to infinity, negative 1 to the n, x to the 4n plus 1, divide by 4n plus 1 times 2n factorial. So that is a series, so it's the series. And there's the answer to the first part of the question. Okay, so take something that looks complicated, replace it with the Taylor series. Now you have something polynomial. And we have ways to do that. All right, are we good with the first part of the question? Because there's a second part. The second part. Get an estimate for the integral from 0 to 1 of cosine t squared dt, which is within 0.001 of the actual value. So within 1 over 1,000. So we want to find a number that is close, within 1 over 1,000. And we want to be able to say, yes, we can justify it. And what does this have to do with that? Are they tied together? Is there any connection between these two parts? The integral from 0 to x of cosine t squared dt versus the integral from 0 to 1 of cosine t squared dt. It's almost like you want to cross your eyes and be like, spot the difference between these two. What's the difference? Yeah, the 1 versus the x. So we say, okay. So the integral from 0 to 1 of cosine t squared dt, we just take this and plug in x equals 1. So that's the sum n equals 0 to infinity minus 1 to the n. 1 to the power of 4n plus 1, also known as 1. Divide by 4n plus 1 times 2n factorial. Now, let's make an observation here. Minus 1 to the n. What kind of series has minus 1 to the n? Alternating. And if you took the exam, you might remember something about alternating series. We have error bounds for those. So what we can do, what are we looking for? Our error bound is, we're looking for where to stop our sum. Our error bound is the size of the next term. So let's write down some terms. We can plug in 0. If you plug in 0, upstairs you get 1. Downstairs you get 0 plus 1, which is 1, 0 factorial, which is 1. Okay, so we have 1 over 1. Minus, okay, because n equals 1, there's going to be a minus. 1 over 5, so that's 4 plus 1. And then 2 factorial, which is 2. Now, is 1 over 10 smaller than 0.001? No. Okay, so we keep going. Plus, because we're at n equals 2, minus 1 squared. Downstairs, we'll have 4 times 2 plus 1 is 9 times 4 factorial. 4 factorial? 24. Okay, is this smaller than 1 over 1,000? No. So we'll keep going. Minus, because now we're up to 3. 1 over 4 times 3 plus 1, 13. Times 6 factorial, which is a number, 720. Now, is 13 times 720, how does that compare to, and as we said here, this is 1 over 1,000. Is 13 times 720 smaller than 1,000 or bigger than 1,000? Yeah, so the punchline here, this is less than 1 over 1,000, which means if we stop at that point, our error is less than the next term. So, to be within 0.001 of the correct answer, we just have to add up 3 numbers. Now you're probably thinking, okay, why is that cool? Well, we talked about numerical integration before, and we said that's a way we can go about finding approximations. If we tried to do this with numerical integration, we'd have to add up not 3 numbers, we probably would have to add up hundreds of numbers before we could guarantee our accuracy. So 3 is a pretty good amount of numbers. That's something we can do almost by hand. So, all right, let's see, how much time do we have? Oh, we have time to do one more. Any questions on this one before we do our last problem? Yes? Well, why do we only integrate the t part? Because our integral is a dt integral. So anything that doesn't involve a t is a constant. So in particular, you might say, well, wait a second, isn't n changing? Well, it does change, but the n changes with the sum, not with the integral. The integral only looks at the t. So I only have to say, as far as integral goes, anything with n is a constant, so that's why it comes out of the integral. The only thing that needs to stay is things with t in it. Anything else? It's good to ask questions. Better to ask them before the final than after. All right. Our last problem for the day. Not our last problem for the semester, but our last problem for the day. Let R be the region, x going from 0 to 2, and y going from 0 up to e to the minus x squared. Now, if you've taken any statistics course, you probably have seen this function e to the minus x squared before. It's sometimes referred to as the bell curve and Gaussian distribution. It's essentially what statistics is based off of. They said, I really like this curve, and so we're going to make a whole discipline based off of this curve. But it turns out that besides being a beautiful curve to look at, it's a really hard curve to integrate. E to the minus x squared has no nice antiderivative in the sense that if you try to write it in terms of exponential or polynomial or sines or cosines or arctangents, if you use the basic functions we've talked about, there's no way to write the antiderivative of e to the minus x squared. Now, it's not that there doesn't exist one. There does exist one. That's the theory. Fundamental theory of calculus tells us there is an antiderivative. It's just not one we can write with the functions we have. And statistics says, okay, we'll just make a new function. We'll call it ERF. And then you have the ERF function. And, but before that, okay, how do we get computations done? Well, we have our ways. So we have this region, it's been shaded here, and we're asked to find the volume resulting from spinning around the x-axis, so we're spinning here. Express your answer as a series. So we're going to get our answer as a series, which means we're going to use Taylor's series to answer the question. Okay, so first thing, we're asked to find a volume. Okay, throwback. And we're going around the x-axis. So first thing we should do is set up our volume. Now, because of the way our region is described, it's y is a function of x, we're tempted to say we should slice in this way. So we have our little tiny dx here, and we have our vertical slicing. And there's a question you have to ask. What's the right technique? Because we learned a couple of techniques for finding volume. One of them being disk washer, another one being shell. Which one are we? Washer. Because what you can do is you can say, I know how we're spinning, so I spin it, and I look at the shape. And the shape that comes out is a disk. So a washer is a disk without a hole. Or sorry, a washer is a disk with a hole. So it's the disk washer method. And conveniently for us, we have that at our fingertips. So we say, okay, volume is the integral, start to finish, pi, and we have our big radius squared minus our little radius squared, and what we call thickness. Now in our case, the thickness is the change in x, because we're slicing. The little radius is 0. What's the big radius? E to the negative x squared. Okay, so, and I should point out that a and b are 0 and 2. So we have integral 0 to 2, e to the negative x squared, oh, don't forget the pi, e to the negative x squared squared dx. Or we have the integral 0 to 2 pi e to the minus 2x squared. All right, now I just went on a rant about how e to the minus x squared doesn't have a nice antiderivative. What about e to the minus 2x squared? Same rant, so I won't give it again. It's just hopeless. But that's not the point here, right? When we see as a series, we say, hey, can we rewrite this as a series? Well, are any of our Taylor series going to be helpful here? Yeah, there's an e here. And we look and we say, well, what's in our box? Minus 2x squared. So we say, cool. So now we're ready to do some work. We say, all right, this becomes equal to the integral 0 to 2 pi sum n equals 0 to infinity minus 2x squared, this is our box, to the n over n factorial dx. Okay, so that's integral 0 to 2, and I'm just going to do one quick thing, rewrite this. This is minus 2 to the nth power, because I can take the nth power and distribute it, x squared to the nth power, x to the 2n. All right, what comes next? We integrate. How do we integrate? Bring in the integral. Integrate term by term. So this becomes the integral, sorry, not the integral, pi times the summation n equals 0 to infinity. Anything without an x, as we're integrating with respect to x, I'll just leave outside the integral. So you have minus 2 to the n, or n factorial, integral 0 to 2 of x to the 2n dx. All right. Well, let's do that integral to the side here. Integral 0 to 2 of x to the power 2n dx. What does this become? X to the 2n plus 1 over 2n plus 1. Evaluate from 0 to 2. Well, good news, when you plug in 0, you get 0. When you plug in 2, what do you get? 2 to the power 2n plus 1 over 2n plus 1. All right. Well, so we plug this in. So we had our pi sum n equals 0 to infinity. I'm going to go ahead and do one more thing here. This minus 2 to the n is minus 1 to the n, 2 to the n. Then we're going to times it by 2 to the 2n plus 1. Divide by, there's a 2n plus 1, and then there's also an n factorial. Now this is good enough for points, but I just want to know what's one more thing we can do. I have these 2's. 2 to the n times 2 to the power 2n plus 1 becomes 2 to the power, well, you add the exponents, n plus 2n is 3n plus 1. Divide by 2n plus 1, n factorial. And there we go. That is a series. The value of that, it's a number, right? Because there's no x, there's no variable. So once you find that number, that is the volume. And so we found the answer of the volume, and we wrote it as a series.